All right, so the question was why sodium positive has a positive charge, and you have to answer it. So look at your answers, and if you have talked about charge in general, like if you've said that protons are positive and electrons are negative, give yourself 1 mark. Now for the second part, if you mentioned that this has more protons than electrons, you have talked about that this has less electrons than protons, then give yourself another mark. And that is how you get to answer this question. So that is why anything has a positive or negative charge. There are many other information that you can give it. I know that you guys have been studying chemistry for a couple of years now, most of you, and you have so much information that you want to share with the examiner and you want to tell them that I know chemistry, but everything has its place. So in this answer, if you start talking about where those electrons are or how those electrons are arranged, that is quite irrelevant. That's not required. So you just have to talk about protons, electrons in general. If you want to say how many they are, sure, go ahead. If you don't, that is also fine. But nothing warrants using the information of where they are. Okay, so that's not required. All right, so here is another question, another particle that I want you to look at, and I want you to find out how many protons, neutrons, and electrons it has. So this one is BE49. So these numbers, they mean something. This one is nucleon number, and this one is proton number. For the last 2 years, what Cambridge has done is that they have written the proton number on top and nucleon number at the bottom, like this. If they were to write this in the exam now, they'll probably write it like that. But it doesn't matter because we know that the smaller number is the proton number. Now use this information and find out how many neutrons, how many protons, and how many electrons it has. Go ahead. All right, so this one should be pretty simple. Remember that proton number is the number of protons. So we write 4 there. And to find neutron, you just subtract the two numbers. So you subtract the smaller from the larger, you get 9 minus 4, which is 5. So this thing has 5 neutrons. And the electrons are basically charge subtracted from proton. So proton minus charge. This one does not have a charge. It is 0. Now, if the charge is not written, we'll take that to be 0. So protons minus charge, that is 4. So this has 4 protons, 4 electrons, 9 uh, total mass, out of which 5 is from neutrons. Now here's another one. Now this one has a charge. Now use this to find out how many neutrons, protons, and electrons this thing has. So a few students have sent me their answers. Good work, you guys, because so far all the answers I've received are correct. Good work. So let's do it. The number of protons here is going to be equal to the proton number. So proton number, as you can see, is 16. It's the smaller of the two. So 16 over there. Neutron number is the difference between mass number and the proton number. So 31 minus 16 gives me 15. And the electron number is basically protons minus charge. 16 protons minus the charge, which is -2, -2 becomes positive, and that means I'll have 18 electrons in this thing. All right, so that's how you find out the number of subatomic particles that anything has. And here's the thing. Sometimes you get some particles which have the same number of protons. Like some of these numbers may be same. For example, you can have what we call isotopes. So here's some isotope that I want to share with you. This is the simplest of the isotopes that we have found so far over here. Now, okay. So this one, as you can see, I'm using the same symbols as before. Red is neutron, proton is blue, and electron is negative green. Okay, so here you can see those. Let's see how many protons and electrons this thing has. Similarities: 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, 1 electron. These are similarities in these things. This proton number being same is special because what it means is that they are the same element. Okay, and element is a term that we'll talk about later on, but for now just know that this is the purest of the things that you get naturally. So all these atoms have 1 proton, and that's a special fact about them, that they are from the same element. This element has a name. This one is called hydrogen because it has 1 proton, and that's the symbol for it. Now the differences: no neutrons, 1 neutron, 2 neutron. Now adding neutron makes it heavier. Adding neutron makes it boil at a slightly different temperature. In fact, not really. Uh, Adding neutron makes it less volatile, slightly. And there are some other factors that it plays or that it introduces to the atom, which are not related to our syllabus. For example, if you're studying nuclear physics, you will definitely study about that. But these neutrons, they just make it heavier for us. That's the context that we are working in. Now, chemical properties of anything come from these green particles outside, the electrons. Now, these neutrons haven't done anything to that. You can see that the electrons are still the same for these. That means same chemical properties in these things. Okay. And maybe some physical properties will change, but the chemical properties are going to be exactly identical, which means if I gave you these three kinds of atoms and I ask you to burn them or to react them in something, you will not be able to tell that you just use different kinds of atoms because they'll behave exactly the same when it comes to reactions. So these things are called isotopes. They have same chemical properties, they have same proton number, they're the same element, in fact, but the difference is they have different number of neutrons. Okay, and that number of neutrons is what makes the difference. So this one, all of them are hydrogen, and we cannot say that which one is more hydrogen than the other one. That's not the same, because I've seen students say that the original hydrogen does not have any neutron. That's not the case. They're all as original as hydrogen comes. It's just that one comes in a flavor that doesn't have any neutrons and one comes in a flavor that has two neutrons. And that's about it. That's what makes anything isotope. Now, there are elements for which we haven't found isotopes. So here are some examples of isotopes that I've found. So this thing over here, this graph, this is supposed to show us different isotopes. So these numbers in the middle, they're showing different masses. So fluorine, for example, all of it is green, which means all the atoms found in nature so far for fluorine have a mass of 19. That means fluorine just comes in one isotope, or at least that's what we have found so far. But lithium has two isotopes. One is with a mass of 6, which is shown in this color, which is, I don't know, purple. And then we have 7 in green, which shows that lithium also comes in with a mass of 7. Now, regardless of what mass it has, lithium, if you check the periodic table, it will have a proton number of 3, but the mass will change. So, and the size of these things show how much it changes. And this is called abundance. Abundance is how much of that isotope is present in nature. So for example, over here, lithium, I do not know the exact value, but let's suppose this is basically 10%. Let's suppose it's that, and the rest of it is 90%. I'm not sure, I'm just making it up, okay? But let's suppose 90% of the lithium that you find in nature has a mass of 7, and 10% of it has mass of 6. Now, that means that every time you get lithium, while it behaves in exactly the same way, you might not be satisfied that it has the same mass, or maybe that mass is suitable for a certain application that you want to do. So it's important for us to find average for it so that we don't keep on trying or be lost in finding out which one is 6 and which one is 7. Okay, so that average that we find out is called relative atomic mass, because you see 6 and 7 are mass for lithium, but there are two different kinds of lithium. So relative atomic mass will basically allow us to take one value and then we will be using that value forever. So for example, in this case, how do you find relative atomic mass? So you just take whatever mass it has and you multiply it by its abundance, which is 10% in this case. And then you take the other ones and you multiply it by its abundance. Okay, so 90% in this case. And then you add them up. And of course, the usual laws of BOD mass apply. And you will have what? 6 over 10 plus 63 over 10. And that will give you what? I don't know. I'm not good at this thing. I'm just kidding, I am. So 6.9 And that is the average mass of lithium that you find. Now, once you know the average mass and you're doing calculations, whether you're doing question of moles or anything, you don't have to worry about what isotope you have. You are going to use the average value, and that average value is going to serve you well. Okay, and that's the whole point of getting relative atomic mass, apart from a couple of other things. Okay, so this one has an average mass of 6.9. Now, this is an oft repeated example, chlorine. Chlorine has two isotopes that we found in nature. One is 37, which is 25%, and the other is 35, which is 75%. And you can easily find out different values for these isotopes, but relative atomic mass makes it very easy for us to find the total mass of anything or to use it in calculation. You just have to take the mass and multiply it by its abundance. So here's an example I want you to do. Krypton comes in 4 different isotopes. Now let's suppose I'm going to assign these values randomly, okay? So let's suppose 86 is 20% and 83 is also 20%. 82 is also 20% and 83 is 15%. Okay, so 83 is 15%. And the rest of it, we do not know what it is. The rest of it is 84. Okay, now, can you please find out the average mass of Krypton? All right, so that should be good enough time. Let's try to solve it together. The first thing we need to know is how much is the 84% one? So remember the total percentage is always 100%. So 20 there, that's 40, 40 plus 15, that's 55. You subtract 55 from 100 and you'll get 45%. So that is for 84. Now, what do we have to do? To find the relative atomic mass, you just take mass and you multiply by percentage, mass by percentage every time. So 15% by 83, mass by percentage, mass by percentage. There you go, mass by percentage. You just multiply it every time and you just add it up at the end. Now, I don't have a calculator, so I'm going to rely on you guys. Another way to do this is that instead of having to divide by fractions, you simply do this: 82 times 0.2 plus 0.15 times 83 plus 84 times 0.45 plus 86 into 0.2. Now, why I'm doing this is because I've converted 15 over 100 to a fraction, which is 0.15. All right. So using this, I will be able to calculate whatever the value is. 83.85, which will round off to 83.9. 3 significant figures is what we are required to use. So 83.9, that is going to be our relative atomic mass for this thing. Now, in the beginning of the lesson, I told you that this atom, the one that has 6 protons, many scientists hold it dear. And where did it go? Yeah, this one. So this one is basically carbon 12. And why it is special is that there's a technique that is used to find relative atomic masses. And when they did it for all the different ones, they found out that carbon takes a high value of 12, like most of it, the high percentage is for 12. So they just took that to be the standard. And now every other atom is basically weighed against carbon 12. So that's just an idea that you need to remember, that whenever the word relative comes in, it's going to be compared with carbon 12, the isotope of carbon that has mass of 12 in it, which means that when I say lithium has a mass of 4, then what I'm actually saying is that that lithium atom or that isotope of lithium is 1/3 the mass of carbon 12, because carbon is 12, so 3 lithium will equal to 1 carbon 12 or something like that. Basically, we're comparing everything with that, and that's just an idea you need to remember. There's nothing related to it when it comes to your exam, apart from the fact that that goes into the definition. So what's the definition? The definition of relative atomic mass is the mass of an atom compared with carbon 12. Okay, to answer this question, that wouldn't it affect the accuracy of these things? Usually we round it off to 3 significant figures in O levels, which is good enough accuracy for us, to good enough precision for us. But later on, for example, in O levels, everything is rounded off to, even the relative atomic mass is rounded off to 1 decimal place, and that increases the overall precision of things. And later on, if you go into university or anything, there the applications might be different, so people won't round it off to just 2 significant figures or 3. So depending on how you round it off, you will be able to find the average. Okay. The advantages of finding average outweigh the advantage of not using it. That is why people prefer it in any way. All right. So we have talked about neutrons. We have talked about protons. Now it's time for electrons. Okay. So what do electrons do? They reside around the atom. Now, why we are going to study them? In fact, we are going to study them more than we study any other part of atom, because they are the ones that govern the chemical properties of things. They are the ones that make things behave in a certain way. Even though they're small, they have high impact. So what do electrons do? First of all, electrons go around the nucleus. They are moving at fast speed in what we call a cloud. Now, that cloud can have electrons added to it, and it can have electrons removed from it because it's outside. Okay, electrons are outside. They are easy to access comparatively compared to protons and neutrons. Protons and neutrons are going to reside right in the middle of the atom, and they're going to be hard to access, but electrons are not. That means you can access these electrons and you can add or decrease the number of these things, and which will affect the properties of these things. These properties, we call them chemical properties. Now, chemical properties come from a special kind of electron, the ones that are outermost. Okay, and we have a word for it. We call them valence electrons. So valence electrons determine chemical properties. Now, what does that mean? That means all isotopes will have the same chemical properties. Why? Because they have the same number of protons and electrons. The only difference is neutrons. So neutrons have nothing to do with chemical properties. That is why we are only going to consider valence electrons when it comes to proton. But why are valence electrons important? For that, we have to know what one thing that is called electronic configuration. Okay, so the idea goes like this: that atom has these electrons in different levels, or what we call energy levels. Okay, and energy levels are also called shells. All right, so these electrons go into these shells, but these shells have limited space in them. There's only a limited amount of electrons that they can accommodate. First shell can have up to 2 electrons. That means that's the space it has. Second shell can have up to 8. Third can have up to 18, but prefers to do 8. Fourth can have up to 18, but prefers to do 8. Okay. Now in IGCSE, what they do is that they usually give you some random numbers in there. For example, they might give you 2, 8, 18, and 3. Don't be afraid of it. That what is this 18 doing? Because you see, chemistry is all about the valence electron. So we're only going to consider that one. Sometimes they give you something that has so many of these shells, but it doesn't matter. Now, O-level people have it easy because what it means is that they only have to deal with up to 4 electrons, and they are also gentle with them, that only 1, 2, or up to 8 numbers, no more 18 or those numbers there. So nothing to freak you out there. All right, so these shells, which I'm going to call them, they tell us how big an atom is. Bigger atom means that they have more shells. Okay, and how does it relate to the periodic table? The number of shells tell us the number of period for an atom. Now, every atom has a certain number of shells, and you will find it in that period in the periodic table. How do you find the period in the periodic table? It's the row in there. So fifth row, fifth period, 5 shells. Fourth row, fourth period, 4 shells. Okay, that's how we know. Now the last electron, last shell, as I told you, is special. For example, in this case, let's suppose we have this one. So this is the last one. In this one, this is the last one. And these are called valence electrons. And valence electrons tell us the group number of things in the periodic table. Group is basically the column. Okay, so from top to bottom, vertical lines. So this one, the first atom, let me call it A, and the second one, let me call it X. A has 3 shells, and it has 8 valence electrons. What does that mean? It is going to be in the third row or third period, and it's going to be in the 8th column or group 8 of the periodic table. Okay, so looking at the electronic configuration, we can find out where an atom resides in the periodic table. X over here has 4 shells, and it has 2 in the last shell. So 2 valence electrons and 4 shells in total. It's going to be in the fourth period or fourth row of the periodic table, and it's going to be in the second column of the periodic table. So you can find out that it's going to be over there. Now, what about the inner ones? The inners are actually complete. You will notice that they're always 2 or 8 if they're not the valence one. And why is that? That is because what we call octet rule. Octet rule tells us that and a shell is stable if it has numbers that are if it has shells that are 0 or 8 electrons in them. So what that means is that every atom aspires to be stable. Every atom tries to have that thing. And if something actually achieves it, we call it that it has achieved noble gas configuration. Okay, so noble gas configuration is when there is 0 or 8 electrons in valence shell. So that's what they want to have. So what do? They either gain electrons or they lose electrons. Okay, and that's what we're going to study tomorrow. But today we are going to just consider what that does to the atom. So let's suppose I have this 282 example. Now this atom is basically what? Magnesium? Yeah. So magnesium has this configuration. How did I do it? I just put them in the first shell up till I got the number 2. The remaining atoms, I put them, remaining electrons, I put them in the second shell until I got to 8, and the third one to 2. Like if I was to redo it, magnesium has 12 electrons because I found it in the periodic table, 12 protons, 12 electrons. They're going to be, in the first one, there's going to be up to 8. So I'm left with 10 electrons out of 12. Out of those 10, 8 are going to be in the second shell. I'm left with 2 electrons that go into the third shell. Okay. Now, magnesium wants to be more stable. Not to say that it is unstable. It is stable, but it can be more stable if it attains noble gas configuration. So how will it do that? It can either go to 0 or 8 in the last shell. If it goes to 0, that would mean it has to lose these 2 electrons. To lose these 2 electrons, I can write magnesium minus 2 electrons makes magnesium get a positive, negative, positive. What charge will it have? Positive or negative? It's losing electrons, right? So electrons take the negative charge with it. So right now it's at 0, it goes to positive 2. It means it has lost 2 electrons. So lost 2 electron, magnesium minus 2 electrons makes magnesium 2 positive. It is also possible that magnesium goes the other route and it gains 6 electrons, magnesium and 6 electrons, and they make what we call magnesium will have now 6 negative charge on it because every electron that comes in brings negative charge with it. Okay, for some reason, chemists don't like the negative sign, except if it's in the charge. So we'll bring that thing over there and we'll put it plus 2 electrons over here. Okay, so what does it mean? It means magnesium atom changed to magnesium with a positive 2 charge. Why? Because it lost 2 electrons. The second row we'll read it as magnesium and 6 electrons combined, and they made magnesium with a 6 negative charge. Now remember, electrons are expensive. So this will require more energy and this will require less energy. So this is good. So we're going to do that. So magnesium will always prefer 0. And other things like chlorine, which has 17 in electrons and 7 in the last shell, it will try to gain 1 electron and become chlorine negative every time because that takes less energy because it wants to get to 8. So some things prefer 8, something prefers 0. Things that always prefer 8, we call them non-metals. And things that always prefer 0, we call them metals. Okay, so metals will always lose electrons and get to 0 in the last shell, and non-metals will always gain electron and get to 8 in the last shell. There are other added things over there. Every time something gains electrons, it basically becomes more negative, and that thing we'll call an ion. So overall, these are ions. This is ion, this is ion, but this one we'll call cation because it's positive, and this one we'll call anion as it's negative. So cations are the ones that have what you call positive charge, and anions are the ones that have negative charge. Okay, now group 4 is basically undecided. The first 2 elements in the group 4, they always gain electrons and they go to 8. But as you go down the group, the atoms become bigger and it gets difficult to gain electrons. So they start to lose as well because 4 can go to either side. It's a swing state. Okay. So that is why sometimes if the atom is small enough and it's able to attract these electrons, they will gain electrons and they will become negative. But if the atom is really big and it's difficult to gain electrons, it will change that and it will go to become negative. All right. So that is what the fourth one do. Okay. So there's a part in there that we call non-metal and there's a part in there that we call metal. So I'm going to take you to periodic table now and we will see how we arrange them. All right, so over here, there's a staircase that's important. So in this case, there's a staircase happening like this. So if you notice, what's happening is that things that are on the right side of the periodic table always prefer 8, most of the time, in fact, and things on the left side always prefer 0. So they are metals, the left ones. So they are metals on this side and non-metals on that side. There's some parts that prefer not to still behave like metals, like because this is one property that defines metal. There are many others. So some non-metals try to act like metals in some context, like they conduct electricity or something, which we'll call metalloid. So this one is a metalloid, this one is a metalloid. Okay, but you just need to remember about silicon. Okay, now how does this relate? The charge, how does it relate to the group number? Group 1 will lose 1 electron and become 0. So that means 1 positive every time. This will become 2 positive. This will become 3 positive. This will become 1 negative because it's gaining 1 electron. It has 7. It gains 1 electron, becomes that. Group 6 gains 2 electrons, so becomes 2 negative. Group 5 gains 3 electrons, become 3 negative. Why? Because it wants to get to 8. 0 or 8. Those are the two preferences that I have. Group 4 sometimes makes 4 positive, sometimes 4 negative, and in some special cases, 2 positive. There's some that you need to memorize, and I will send you a fact sheet. I have exams this week, but after this week, I will send you a fact sheet to remember, in which I'll tell you which atom will lose which ones. Now, what you need to know is to be able to write electronic configuration of the first 20 elements and to convert them to noble gas structure. Now, here's a fact that I want to share with you. Remember that periodic table lists atom in terms of their proton number, which means carbon has 6 protons because that's why it's here, and nitrogen has 7, that's why it is. So here's the thing. Every atom can take electrons and become like some other atom. So carbon over here, for example, if I gave 1 electron to carbon, it will behave like nitrogen because it gained 1 electron. It will become C negative 1. Similarly, if I took 1 electron from carbon, it will start to behave like boron. It will be C positive 1. So here's a question. Can we find out 3 atoms which can have different charges and behave like aluminium? This one over here. Can you find 3 atoms? So give me an atom and I'll tell you what we have to do to it so that it starts behaving like aluminum. Anybody? Take a wild guess. Your favorite ones. Okay, so let's start with the first one that we got, magnesium. Okay, so let's see what do we have to do to magnesium so that it starts to behave like aluminum. So magnesium, silicon. We are going to do with 2 examples. All right, so over here we have magnesium. Magnesium has 12 electrons. I'm only talking about electrons, remember. And aluminum has 13. So what do we have to do? Magnesium will gain 1 electron and it will become negative 1 and it starts behaving like aluminum because this has 13 electrons. This has 13 electrons. That's it. Chemical properties, same. All right. The other example somebody gave was silicon. Silicon has 14 electrons. So if I want to make it behave like aluminum, I just remove 1 electron from it. So 14 minus 1, 13. So that means positive 1 charge. You're removing an electron. This also has 13 electrons. Now, when everything does this, they don't try to become like aluminum. Their favorite ones are over here. Group 8, noble gases. Okay. These elements, they have a class issue. Okay. They want to behave like noble gases. So what happens is that every atom tries to gain or lose electrons based on how close it is to the noble gases. For example, beryllium over here, it's in group 2, which means it has 2 in the last shell. So it will lose 2, hop 2 spaces back and behave like a helium. And nitrogen over here, it can hop 3 steps up and start behaving like neon. And that means it will gain 3 electrons. Okay, so that is what they do. They always try to mimic their nearest noble gas. And to do that, they have to gain or lose electrons based on how far away they are. For example, in the case of aluminium, aluminium will have to go 3 spaces back and become like neon, or it can go 5 steps forward and become like argon. Calcium, it can go 2 steps back and become like argon, and potassium can go 1 step back and become like argon. Okay, so that is how these atoms attain noble gas configuration, and that is how they become positive or negative ions, which we call cations and anions. Okay, and with that, I would like to end the lesson for today.